So what I wanted to do was go ahead and now go back over the lecture we had on Tuesday and give you guys a walkthrough up to the point where you could be able to work on the project that I posted yesterday. So just to review where we are, we're still talking about combinational circuits, which is made up of gates. We're about ready to migrate to sequential logic, where we'll be dealing with flip-flops. We'll introduce the concept of a clock. But what we're talking about now are circuits that are just made up of gates, AND gates, OR gates, exclusive OR gates, inverters. What we've been doing so far has been fairly simple, just learning how to build certain circuits up, how to define them with truth tables, timing diagrams, how to simplify them using Carnot maps. But what we want to do now is to move on to implementing a little bit more interesting circuits. Before we leave the combinational logic, first I want to point out in these couple charts where we talk about when you see a combinational array, initially it may appear to be overly complex, but by breaking it down to the intermediate nodes, you can simplify your evaluation of the circuit fairly easily. So for instance, T1 here would just be B bar ANDed with C. T3 would be A ORed with B bar ANDed with C, and so on. So this would be what I call the logic diagram or the detailed circuit implementation. Down below we see the top level block diagram where all we show are the 4 inputs and the 2 outputs, and then the guts of it need to be defined elsewhere. So this shows a little bit more how you could do that parsing of the circuit to see what's going on. And also here you can study this on your own time and you can see exactly how each node is evaluated and how you can then deduce what the outputs would be of the final circuit. What we want to do now is look at the applications, or specific application of combinational logic. And the first one we're going to do is come back to our adder subtractor, although the very first thing we're going to talk about is the adder. And what I find interesting is this transition of having learned about all these logical operations and the logical elements, that now you can combine them in such a way to do arithmetic operations. So the first arithmetic operation we'll do is an addition, and we'll follow on that with a subtract. So just to help us understand the circuit, when you do addition or subtraction, you're always dealing with columns. And if you're doing an addition, you add the 2 arguments for the column, but you always need to consider what if I have a carry in from the previous column, and then what if I have a carry out. So in our implementation we talk about a carry in and a carry out. That's allowing us to do column based math. So now we want to see how we combine these logical elements. The first that we'll look at, which we talked about in class, is what's called the half adder. And it basically just sets the tone for what we want to do. Where we want to get to is the full adder, where we'll be able to construct an n-bit adder by concatenating together these full adders. So the half adder, we see there's 2 inputs, x and y, 2 outputs, carry and sum. We create the truth table like we always have, showing every possible combination of inputs. Then the outputs, we just generated according. So 0 plus 0 is 0 with a carry of 0. 0 plus 1 is 1 with a carry of 0. 1 plus 0 is 1 with a carry of 0. And then 1 plus 1 is 0 with a carry of 1. So we can see by observation looking at the truth table that the carry could be implemented with an AND gate. The sum could be implemented with an exclusive OR gate. So now what we have is, howbeit a very simple circuit, but it is a circuit that begins to give us a very rudimentary form of addition. The full adder now We add in the concept of a carry-in, which gives us now 3 inputs, which is why we have 8 rows. And now the carry out and the sum are the same game. 0 plus 0 plus 0 has a sum of 0 with a carry out of 1. 0 plus 0 plus 1 has a sum of 1 with a carry out of 0, and so on, until you're adding 1 plus 1 plus 1, where we have a sum of 1 and a carry of 1. And if we utilize the cardinal maps that we've learned about to try and come up with a simplified implementation of these expressions, we quickly see that the carry out is the OR of the AND of each of the terms, and it turns out that the sum is the exclusive OR. Keeping in mind that exclusive OR is where an odd number of ones on the input can maybe found. So there is the truth tables, and here is how I would implement it. My carry is the AND of the 3 terms, and then the sum is the exclusive OR of those terms. Then what we could do, we could build a half adder cell. This is our top level diagram where we have our inputs A and B, the input carry in, an output carry out, and an output sum. And what we can see now is how we can concatenate these together to build our n-bit adder. So we're going to hook them together. We'll see that we call this type of adder a ripple carry adder, but that we'll discuss when I get back on Tuesday. Exactly what does it mean, a ripple adder, ripple carry adder. So what we're going to do is we're going to create first a 4-bit adder, which takes 4 full adders, distributes the data input A and B to the 4 adders, generates the output sum from the 4 adders. The carry out comes out of the most significant stage, and the least significant carry in has a 0. We can then abstract that as a 4-bit adder cell, and now we have a building block that we can create what we call hierarchical designs, where we've created the full adder. Now we use 4 full adders to create a 4-bit adder, and then the next what we're going to do is use 4 4-bit adders to create a 16-bit adder. And the top level block diagram again shows 16 bits on A, 16 bits on B, single bit carry in, single bit carry out, and then a 16-bit sum. And again, we build it by concatenating together 4 4-bit adders, distributing the inputs to each of the 4-bit adders appropriately, generating the sum appropriately out of each of the 4-bit adders, bringing a carry in of 0. Since we're doing an add, we don't want the carry in to be set, and we generate a carry out. So that is the 16-bit adder that I discussed in the lab presentation that I posted yesterday. The last portion, which you'll not do in your lab, but I would like you to be thinking about it before we get to class on Tuesday, is that now, recalling how a 2's complement works, that we can generate a negative value by complementing all the bits and adding 1. So now we could take a positive value and turn it into a negative value. And how will we use that? We've just built a circuit that allows us to add 2 numbers together. And if you recall, subtraction of A minus B is really the same as A plus a minus B. So we're still going to use our basic adder, but instead what we're going to do is we're going to bring in a negative B when we want to perform the subtraction. So here again, to remind you, the most significant bit of a 2's complement value is the sign bit. The other bits tell us the value. And we recall when we represent them, for us we're going to have a 16-bit value. Again, this is review of what we've discussed in class. You can study it just to make sure you recall exactly what a 2's complement is. And finally, what do? We take our 16-bit adder that we've created out of the 4-bit adders. We bring in the A and we distribute it to the 16-bit adder. But the B input, we add a multiplexer. And the multiplexer has a select that tells us if we're adding, it's a 0. If we're subtracting, it's a 1. So if we're adding, we pass B right through the multiplexer to the B side of the adder, and the sum would give us A plus B. If we want to subtract B from A, what we do is we select the other side of the mux, which now complements all of the bits of B, and distributes it to the inputs. Now, if you recall, a negative B is not just the complement, but it's a complement plus 1. So what we do is we take that select bit from the mux and we run it to the carry in of the least significant stage. So now when we want to perform our subtraction, what we're doing is we're adding A to B complemented plus 1, which in the end will give us our A minus B. So I'm going to stop the lecture now. I don't expect you to implement the subtraction portion by Tuesday, but it would be wonderful if you could have the adder created like presented in the video done by Tuesday. Thank you very much. See you guys on Tuesday.